Hello, this is the seventh in the series of videos on random numbers, accompanying the book Random Number Generators, Principles and Practices. And we've looked at entropy sources in some detail. Now we're moving on to entropy extractors. And first we're going to look at entropy itself and some definitions of entropy and how those definitions are necessary for defining what an entropy extractor is. So most of this video will be on defining entropy and then the definition of an entropy extractor as a function of the definition of entropy. Basically, an entropy extractor takes some partially entropic source, so it's not perfectly random, and makes it more random, hopefully perfectly random. But when we get into more detail on these things, we'll find out that's actually impossible. You can just get close. So this is the first in the entropy extractor videos and the seventh in the series. And I'll take a look towards the end of this on how entropy extraction is actually very similar to alcohol distillation, which I find quite humorous. So here we are. We're looking at definitions of entropy and entropy extractors. We'll go on to look at some trivial extractors, things like XOR gates, which will help us understand how more effective entropy extractors work. Single input extractors, seeded extractors, the extractors in SP 100-90B, and probably a few other related topics. So there's a paper by Alfred Renier called On Measures of Entropy and Information. And in it, he defines a measure of entropy, or a generalized measure of entropy, over a probability mass function, or a probability distribution function, depending on how many p's you have in this. So X is a set of probabilities. You can consider it ordered, but it doesn't matter. And it's just a probability distribution. Each probability is giving you the probability of an event. So you have some random source X and it's spitting out numbers, and it can spit out n different numbers, and this is the list of the probabilities of each of those n numbers occurring. And he defines this function big H sub alpha over that distribution, which is big H sub alpha over those probabilities that define the set of probabilities of the distribution. And that function is 1 over 1 minus alpha of log of the sum of the probabilities raised to the power alpha. Now, obviously, alpha cannot be 1 because 1 minus 1 would be 0, and you'd have a divide by 0 problem. And it should be greater than or equal than 0, not non-negative. So when you plug in alpha, you've got some commonly used values for alpha. 0 is what's called Hartley entropy or max entropy. And that's just a definition of what is the maximum entropy that a set of bits could hold. With 1, which I just told you can't have, alpha equals 1, that's what we call Shannon entropy, and we'll take a look at how you actually get to compute Shannon entropy given that alpha equals 1. And you can think of that as a kind of average entropy. It's the weighted average of the entropy of the bits. And this is useful for measuring the information capacity of a communications channel, for example. How much data can you stuff through it? Not very useful for cryptography, though. Then H2 is collision entropy, which is just the probability of two variables taken from the distribution being the same. And then we have H sub infinity, which is called min entropy. And this is the one we care about. And this is the most conservative estimate of entropy. And we'll take a look at that definition too. Now, in the paper by Alfred Renier, there's this interesting part where he says that the limit as alpha tends to 1 of the entropy measure it's easily seen that it is the sum over n of the nth probability log 2 1 over pk. Now, it's not easily seen. It might be easily seen if you're a Renier, Alfred Renier, but not for me. So I worked it out. So my pain is your gain, because I'll show you how it's worked out. You will probably, if you were to, let's go back. Sorry. If you were to look up a definition of Shannon entropy in Wikipedia, you would find this equation here. And you'll see that that's not log P1 or 1 over pk, it's log of pk or pxi in the way they've written it here. Why is that? Well, that's because there's a negative on the front here. So, log of 1 over something is negative something. So, so it's just this formula and this formula are the same. It's just you change the log from 1 over to not 1 over and stick a minus on the front, and it's the same. So let's look at Hartley entropy, the H sub 0 case. That is log 2 of pi to the 0. So 1 over 1 minus alpha is 1 over 1 minus 0 is 1 over 1, so that term goes away. Pi to the power 0 is obviously 1, so the sum of n of those is just n. So this resolves to n, so you get log 2 of n. So when you think about, say, 8 possible values, you can represent that as 3 bits. Log 2 of 8 is 3. So this is really just telling you how many bits does it take to contain that much information. Shannon entropy, this is the one used in communication theory, gets a bit more tricky. So since we cannot plug alpha equals 1 directly into the equation, because that alpha would then put a 0 on the denominator here, we have to take the limit as alpha approaches 1. So we take the limit of 1 over 1 minus alpha of log 2 of that, the equation. And when it does approach 1, when alpha approaches 1, this denominator approaches 0. This thing inside here approaches 1, because if this is pi to the power 1, that's just the sum of pi, and the sum of the probabilities in a distribution is always 1, because something's going to happen with 100% probability. So that's a 1. So log 2 of 1 is 0. And so you get to a situation where you have 0 divided by 0, at which point you should be thinking, well, we'll apply Hopital's rule. And so here we have it, Hopital's rule. And so we go forth doing that. We rearrange it a little bit. So we have this term on top and the 1 minus alpha on the bottom. And then this becomes f alpha, and the denominator becomes g alpha. So that's this. And to get the limit, we want to compute the differential of both the top and the bottom, and divide the one by the other. So so we've got these two definitions for f alpha and g alpha. The denominator is easy. Differential of 1 minus alpha with respect to alpha is minus 1. The numerator is not so easy. We've got a function of a function. If we go back up, we've got a log on the outside of the function, and the inside function is a summation. So we define the outer function v as the log, and the inner function w as the summation. And we're going to multiply the resulting differentials of those two things together to get using the chain rule. And so differential of log alpha is 1 over alpha. The differential of the sum of p to the power alpha is, if you remember your calculus from high school or secondary school, if you're from the UK like me, or wherever you went to school and studied calculus, that becomes the log, and so we get p to the alpha log p in the summation. So we can say that the differential is of the numerator is the differential of the log of the sum of p to the alpha times the sum of p to the x. Well, shouldn't that be p to the alpha log p? And this part here becomes, because it's a log, 1 over that. So this goes into the denominator, and this part, because it's going to 1, the exponent, this becomes just the sum of Pn. So this is the other derivative. So now we can plug those two, put the definition of f of alpha, or the differential of f of alpha on top, and the differential of g alpha on the bottom, and we get this. And we can observe that this term on the denominator of the numerator is just 1, because like we said before, the sum of all the probabilities is 1. And we've got this negative term, so the negative term goes on the front, and we've got the sum of pi log pi. And that is Shannon entropy. So that's how you derive that. When I was writing the book, I wasn't very happy that I couldn't find, Alfred Renier just said, you can easily see this, and then I couldn't actually find a definition, and I spent some time banging my head against the wall trying to get this equation. But okay, so you might have noticed that we were using a natural logarithm there. It doesn't matter what type of log you use, but typically we use log 2, because that gives us our entropy result in bits. If it is a natural log, it's nats, and I think if it is a base 10 log, it's called dits, but nobody ever uses that. And people rarely use nats. Bits is what we use in computer science, because we like bits. So moving on to min entropy, the most conservative entropy estimate. If you try to take the same approach mathematically to compute h sub infinity, it doesn't work. Now, I'm fortunate to have a family member with a PhD in mathematics, and she took a look at the problem and said, "Oh, that's a problem in LP norm theory, or standard result in LP norm theory." So you just do that. Now, I had no clue what LP norm theory is. It turns out it's a generalization of measure in a metric space, which I know a little about. So anyway, if you look at some standard definitions, the LP norm of a set of values is sub p is this, and if p is infinity, it's this, the max of these, and you can plug that straight in, that h sub infinity of x is infinity over 1 minus infinity. So you can think of this as, again, we're taking the limit of this because it turns into a negative, just negative 1. But log 2 of the LP norm over x, which becomes log 2 of the max of the norms, which becomes log 2 of the max of the probabilities. And this is the definition of min entropy in normal probability theory as opposed to LP norms. So there we've had our 4 definitions, and we do not care about these 3. They're not very useful to us. The one we care about is min entropy. This is what's used in all the entropy extraction proofs and the standard requirements for entropy extractors. So we're going to be, when we talk about entropy from now on, we're talking about min entropy. So if min entropy is negative log 2 of the max probability over all I, where I is the index, into the probability mass function, then that intuitively says you're finding the most probable event and taking its logarithm and taking the negative value of that. So here's an arbitrary probability mass function. So if it was continuous, it would be a probability distribution, but this is of discrete values, so it's a probability mass function or called x. And when you look at this, you can see that there are two equiprobable most probable events which have a probability of 0.14, and it happens to be 0.14 because that's what I typed in. I just made this up. But if this were the distribution, you see it has 8 possible outputs from 1 to 8. So as we discussed, log 2 of 8 is 3. The maximum entropy there is 3 bits rather. But we're not going to have the maximum entropy because this is not a uniform distribution. So h sub infinity of x is negative log 2 of 0.14, which is about 2.8365 in each symbol. Each symbol could be represented with 3 bits, which we can see by taking the Hartley entropy. And so the entropy rate, which is a definition of the amount of entropy per bit of data, is 2.8365 over 3. And that's your answer. So that's the entropy we have in data coming from a random source that has this probability distribution. And that's quite a useful thing to know, because when it comes later on to defining the entropy of real entropy sources, it's common to model those with Markov models. And when we do that, we can use the Markov model to define what the most likely sequence is, compute the probability of that most likely sequence, which is then the most probable sequence of bits, and then take negative log 2 of it, and you've got the entropy of the source. So now we know what entropy is. Now, I've not talked in the usual hand-wavy terms, like a measure of disorder or information content. People talk about that, but it never really gets to the mathematical heart of it, which is it is negative log 2 of the most probable event in your distribution. So we then get on to defining an entropy extractor. So we're almost done here. And I'm just going to define the entropy extractor. In further videos, we'll look at actual entropy extractors. We're going to take a number of non-deterministic bits. So they contain some entropy. And the entropy rate is the entropy of the source over the number of bits we're getting from that source. And we'll call that h, little h. It goes through this deterministic algorithm, and this is the extractor. And we're going to say the entropy coming in is not perfect. It's less than 1, and it's not 0. If it was 0, we're wasting our time. So h is somewhere between 0 and 1. And we get out m non-deterministic bits, and they have some entropy rate come out, which is greater than the entropy rate coming in. So we've improved the entropy rate. What you also find is that the amount of entropy out, so h sub infinity of y, the output, is always less than h sub infinity x. So we are not we're not adding any entropy. We're essentially compressing this data so the amount of entropy per bit is greater. Now, m is usually fixed. So if we're using, say, an AES CBC MAC extractor, which is a standardized extractor, the output of AES is always 128. And so the output of AES CBC MAC is always 128 bits. The input can be as long as you like. And in fact, if you have more input, you get a better result at the output, up to some saturating limit. So you can think of this as a compression function or a distillation function, which is what we'll look at next. So we're not creating any more entropy. We are just squishing it so it's more concentrated in the output. The goal, generally in cryptography, is to get non-deterministic bits that are full entropy, where there's 1 bit of entropy per bit of data. That's actually impossible, and we'll look at that in the next video. But we can get arbitrarily close. So that's what we do. We try and get as close as we can, and such that the quality of the entropy is good enough for cryptography, typically. If you're just doing it for statistical purposes rather than cryptographic purposes, you generally don't need to be as close to full entropy. There are algorithms which get close to uniform with much less computational effort, but if you want to get data that's close to full entropy, you tend to need cryptographic algorithms. So this is where we get to the analogy with distillation, which, if you're familiar with distillation, that it should make sense. We're putting in distillation, we're putting in some units of liquid and heat. So we've got liquid coming in and heat going in, and that liquid consists of m units of alcohol and n units of other liquid. So that goes in, and so we can say L is equal to n plus m. And then we output x units of liquid, a smaller amount of liquid, y units of alcohol plus z units of some other liquid. But this should be a more concentrated solution of the alcohol. The y value should be bigger relative to z than m is relative to n. And we get some waste out. We get waste heat energy, we get waste alcohol coming out, and other units of liquid that get distilled off. Some of the alcohol is lost because it binds strongly to water chemically. But what we get out to the other side is a more concentrated body of liquid coming out than was going in. There is no more alcohol coming out than goes in. In fact, there's less alcohol coming out of the useful part. Some of it is wasted. That's exactly the same. These sums are exactly the same with an entropy extraction algorithm. L bits of data, there's n bits of entropy, m bits of entropy, n bits of what I call predictability, for want of a better word. So L equals n plus m. And we're outputting x bits of data that have y bits of entropy and z bits of predictability. And we have some waste output, because this is a computer now, of heat energy, and some of the entropy is lost as heat, and some of the predictable bits are lost as heat. And we're, instead of inputting heat, we're inputting electrical energy, which ultimately turns to heat. So we can understand what entropy extraction is as being like a distillation process. And I would have been happier if it had become the standard thing to call entropy extractors entropy distillation algorithms, because I think it's a much more descriptive term. So that's the end of this video. I'll leave you a flavor of what's coming next. There are multiple different types of entropy extractor, and the three major classes are single input extractors, multiple input extractors, which take independent entropy sources. And then there are seeded extractors, which take their entropy input and a short full entropy input. And this is magic fairyland, because such a thing as a full entropy input doesn't exist. So that's the end of the talk. I'll see you next time, where we'll start looking at simple entropy extractors, and then we'll move on up to real entropy extractors that we actually use. Thank you and goodbye.